right, thanks guys for coming out. A few friends. Should have probably made a more exciting title on the presentation, but thank you guys for showing up. So really appreciate it. I recognize a lot of faces here. There's some new faces. I assume hands up if you're building in Ethereum. Fantastic, great, great, great. And hands up if you just own Ethereum bags. You own some Ethereum. There we go. Okay, fantastic, fantastic. So we're all interested in the future of Ethereum. So let's talk about what that looks like in a world with quantum computers. So to set the context, some facts about quantum computing as an industry. It's a nascent industry, but it's growing pretty quickly. Just in 2023, there were over $30 billion of government investments into the technology, and this is up from $20 billion in 2022. The scary part, I think, is that China dominates this funding with about 2/3 of the $30 billion in 2022. And China isn't the most open with their technology, as opposed to the West, which is more for open science. So that's an uncertainty. And what we do have from the public data that have been released so far, there are many estimates, but one of the papers from the French National Research Lab last summer pointed out that it'll take an estimated 126,000 cat qubits to break 256-bit elliptic curve cryptography, which currently underpins our crypto systems in Ethereum and just most blockchains. How does that look in terms of timelines? There was also a survey to major quantum computing research companies and labs, and they're estimating, for example, IBM is estimating they'll have 100,000 roughly, maybe a little bit less, but they're aiming to have 100,000 qubits by 2030. So we could plausibly feel that within perhaps a decade from now, we would be within this kind of the hot waters of needing to transition to PQC. This is also top of mind for not only for companies, but also governments. The US White House has put out 2 executive orders on initiating quantum initiatives and also transitioning all of their government agencies and also trying to transition American companies to post-quantum, or what they're calling post-quantum cryptography. This has also been talked about by major media outlets. That doesn't necessarily add signal to the noise, but it at least gets the conversation started. So let's talk about it. First, what are quantum computers? Very natural starting point. Well, these are computers that act on what are called qubits. It's kind of their fundamental, it's like their equivalent to our binary bits. These qubits are able to be held in a superposition of states, which means that they can be in a 0 and a 1 at the same time. And one or more qubits can be entangled into a state where essentially if one collapses, it gives you information about another qubit. And quantum computers use the combination of these methods to solve problems exponentially faster. This isn't every problem, but unfortunately it's a problem. They solve the math problems that are most critical to our cryptography. So the way I like to characterize it and think about it is we currently sit in the middle of 2 walls that are shrinking in towards each other. On one side, we have accelerating hardware, where companies are putting more and more research and development into building advanced quantum computers. And we're also getting advancements in the software side, in the algorithm side, where 10 years ago, the number of qubits required to break elliptic curve cryptography was an order of magnitude more than it is today, and who knows what will happen in the next 10 years. So this is all to say that quantum computing affects, or it threatens, our private keys, specifically in blockchains. Many of you will know that every blockchain account consists of a private and public key, and essentially the private key derives a public key for which you sign transactions, and those produce digital signatures, which are then checked against your public key. And the idea is that you're supposed to be able to move from a private key to a public key, but not the other way around. And unfortunately, quantum computers break that assumption via Shor's algorithm, which is a quantum algorithm for finding the discrete logarithm, which effectively kind of breaks ECC. So what is post-quantum cryptography? simply put, it's the same type of cryptography, except that it's just more secure. It essentially handles problems against attacks that we understand quantum computers are able to execute. So we can think about these post-quantum crypto systems as being the exact same, the exact same topologically or kind of functionally. They just use different math problems underpinning them in order to have better security. So let's just say we are able to just implement post-quantum cryptography and reclaim the safety of our private keys. That would be very much ideal, and then we would be done with the situation. But unfortunately, it's a little bit more complex than that, because the algorithms used to generate public and private keys become much more expensive. So these three algorithms on the right, these are the US government soon-to-be standardized algorithms, and ECDSA is what we use right now. And we can immediately see that the smallest NIST standardized algorithm is 10 times, the signature is 10 times larger than ECDSA is. So ECDSA is 66 bytes for the signature. Falcon is 666. And this grows even more towards dilithium and Sphinx, measuring in the few kilobytes. So that's obviously a problem for blockchains. Every transaction is signed, every block is signed. Now we want to pass them around to a massive validator network, and every one of those needs to sign off as well. So how do we combat this issue? Well, first, focusing on the problem. So the BIS, the Bank of International Settlements, they conducted some research on essentially the impacts of post-quantum cryptography on blockchains. And what they measured it through the lens of duration of end-to-end payments and throughput per second. And they found that quantum-safe algorithms, especially using post-quantum cryptography, has much higher end-to-end payments, almost 5 times larger, and then 2 orders of magnitude lower throughput. So this is a huge problem for scaling blockchains, something that we've done so well, I guess, with the vulnerable cryptography today, but something that we'll have to address in the future. So how do we go about this? Well, we've confronted the scaling problem before in blockchain, and we did that through the use of snarks. So let's think about how we can construct snarks in order to solve this post-quantum cryptography problem. There's 2 kind of general ways to construct snarks. The first is using a polynomial interactive oracle proof plus a polynomial commitment scheme. And then you can do a linear probabilistically checkable proof plus some sort of pairing-based crypto. But we know that any pairing-based crypto is vulnerable because it uses elliptic curves. So cancel that out. We can't use that. The next options that we have is looking from this family over here, the polynomial IOP plus PCP. This consists of a polynomial IOP plus a polynomial commitment scheme. And within the family of polynomial commitment schemes, we can't use any of the discrete log-based or the pairing-based because those are also quantum vulnerable. So what we're left with is essentially a much smaller range of snarks that we can build, those that consist of IOPs plus IOP-based polynomial commitment approaches. There's also the possibility of using Starks as well. Starks are hash-based, so they don't fall to these, they're quantum resistant, plausibly. And something just to keep in mind here is that the Starks that we use today are, while the cryptography is hash-based, they follow roughly, like Starkware, for example, uses 80 bits of security, whereas we need to get up to 120, roughly, to be quantum resistant. And so that would be 50x, almost a 50x, I guess, larger proof sizes and also costs for doing Starks today. So this is all to say that quantum-safe snarks and quantum-safe snarks and Starks are possible, but we just need to figure out a good way to build them. So that's kind of the idea for what we're trying to think about at BTQ. We'll just take a moment to think about how we all got here, perhaps. Like, I came from Canada, have some of my colleagues from the Hacker House who came from India and the US and the Netherlands. And in pretty much each one of our countries, I think we all want to see blockchains play a role in our lives. So we really want to touch on every level of the tech stack when thinking about post-quantum blockchain applications. So let's start from we'll start from like the lowest level, talking about blockchain consensus and how we can make that quantum secure, or at least one idea to make it quantum secure. Then we'll move up to like the actual blockchains that we use, and then we can talk about some applications. So one of the ideas that we've been playing around with at BTQ is something called quantum proof of work. This is essentially the same nice kind of proof of work consensus that Bitcoin, I guess, created and Ethereum started off with. And what we're trying to do here is figure out a way to allow people to come together and understand and essentially agree on a set of transactions in a block using quantum algorithms rather than quantum vulnerable cryptography. So kind of putting ourselves on the same playing field as quantum computers. The basic premise, like today's Bitcoin proof of work uses SHA-256 in order to essentially prove that you spent enough, essentially you performed enough work in order to validate this block. And so the analogy here is finding an energy efficient quantum hash function. And it turns out there is a way to do this using a quantum problem. It's called a coarse grain boson sampling problem. You can think about this as essentially one of those fair games. So it's like a game at a fair where you have these pegs and it kind of goes down in a triangle. And you drop in a ring and it kind of pings back and forth, ping pongs, and then it lands in one of the kind of buckets at the bottom. Well, a coarse grain boson sampler does this with photons. And instead of kind of having these rings, you have these beam splitters. And these beam splitters are able to essentially kind of randomly distribute the photon left and right. And so what you end up with at the bottom is this kind of apparently random configuration of where the photons have landed, except it's actually very easy to verify because it's just a quantum problem. So the most important properties of this is that it's actually easy to compute on quantum devices. It's hard to compute classically, so you can't have anybody spoof it. Yet it's still easy to verify on the computers that we have today. So everyone can participate in verifying a block. So what we did is we took a look at like the traditional proof of work and then essentially just tried to replace the aspect for which this proof of, I guess, yeah, the vulnerable cryptography is used. So just as normal, a transaction is created in the network and it's broadcasted to the network and included into a block. And then that block is sent around to all these different miners to generate a proof of to perform proof of work of and verify. And we essentially replaced that with this boson sampling problem, where this block essentially contains its header will define the permutation for all the different the configuration of the boson sampler, and the final permutation, kind of the probability distribution will be essentially then defined by the block header, which is defined by the transactions within it. And so quantum miners essentially try to estimate this, and once someone has found what they think is the right distribution, they send it back to the network, and everybody's able to verify it, and yeah, life goes on as normal. So it's just the same proof of work, but just swapping out SHA-256 with coarse grain boson sampling. And what we found was this is actually far more efficient than doing like hash functions. It's almost 100% cheaper. It takes a few hundred watts to perform this problem, which is far less than the few megawatts that it currently takes in Bitcoin. So we think this is a really nice and an interesting problem, and we're trying to we're trying to build some prototypes and get this out into production. Next, we have this idea for what we're calling layer Q, which is this quantum canary network for Ethereum. Layer Q is essentially a set of software components and libraries, really trying to just kind of focus on replacing ECDSA with some sort of quantum-resistant digital signature algorithm. For this, we chose Falcon. Falcon being one of the NIST standardized digital signature algorithm with the smallest signature size. And what we did was we essentially kind of forked the Ethereum monorepo for their JavaScript library, and then and then kind of implemented Falcon in JavaScript. We also created transaction definitions that use these Falcon signatures, wrote a provider which allows these transactions and wallets to interact with dApps, and then also did signature aggregation on it, so something akin to BLS signatures, where you're able to aggregate over multiple post-quantum digital signatures. And we also forked, I see some Geth guys here, we forked Geth and created our own Falcon Geth client. And all of this is working towards what Vitalik included in his last roadmap, which is this kind of quantum safe SNARK or Stark future for Ethereum. And so one of the ideas that we can start playing around with is having these like quantum safe backups of our wallets, for example. By using account abstraction, we can simply swap out the wallets that use ECDSA, or I suppose more so, we can take a wallet, swap out ECDSA with Falcon, and there you have what's plausibly a quantum resistant wallet. And perhaps the idea would be that everybody has one of these quantum safe wallets and treats it as something like a savings account where they keep most of their tokens and conducts their degen, DeFi trading strategies from their checking account, which is ECDSA still. We can also try things like doing quantum safe multi-sig wallets where you have a quantum, a quantum wallet or contract, and you need the approval of that contract in order to make any transaction. And so this is preventing any quantum adversary from simply deriving your private key and then initiating a transaction from your wallet to theirs. So at least they would need to be able to break both the quantum resistant and quantum vulnerable wallets in order to do so. And then another idea is potentially having this kind of playing off of the staked ETH and the wrapped ETH ideas, where you can stake your ETH and then kind of continue to perform or like earn yield on DeFi. Doing something with kind of layer Q, where perhaps you store your tokens in this quantum safe network, and then you still have access to all of the traditional trading strategies in Ethereum and the L2 ecosystems. Cool. And finally, moving on to the last kind of more high-level application, which is perhaps one of the applications that will affect all of us, which is quantum money, or essentially quantum safe CBDCs. So quantum money isn't a new idea at all. It's essentially this, it was first proposed in the 1970s, and it's just this idea that you have these digital banknotes that can't be forged by a quantum computer. And this is a huge interest to the US government and pretty much every major country who's experimenting with CBDCs. And because they've already kind of publicly acknowledged that quantum computing is a huge threat to their financial cybersecurity industry. But essentially, if anyone is going to be working with digital transactions and digital currencies, they need to be thinking about quantum attacks. So we can think about digital signatures as the equivalent of a security thread on today's banknotes. So when you get like a $100 US bill, you hand it to a shopkeeper, they might look at it through the light and check if it has this seal on it. They're trying to verify that this hasn't been forged and that this has been issued by the central bank or the minting press. And we can think about digital signatures as playing the same kind of role. When you send a transaction to somebody on the internet, they can verify using your digital signature that maybe it was signed by both the central bank and it was signed by your private key to make sure that it was legitimate. So in this idea, or in this scenario, we would simply have this kind of signing utility that for every bank, for every digital currency that's kind of minted, you would simply sign this using post-quantum cryptography and then verify it using the same kind of traditional verification methods we use. But the idea is just that we want to be quantum proofing all of these CBDCs. And yeah, this kind of comes full circle. This idea was proposed by Peter Shor, who also invented Shor's algorithm, the very algorithm that threatens the cryptography that we use. And yeah, and I guess it just speaks to the kind of the nature of the problem. It's kind of, if you're going to have quantum computers, you also got to have quantum money. So the key takeaways is that quantum computing could be the biggest rug pull of blockchains, and upgrades to quantum analogs are imminent. So we should be starting the discussion now. And is it even money if it isn't quantum safe? So thank you very much.
Minutes QA time. Does anybody have questions? It's scary. Any questions? Quantum computing is scary, guys. Any questions? Okay.
Is there any blockchain that is more prepared than another against quantum computing?
Yeah, there are a few quantum-resistant blockchains. QAN network, Abelian, which is kind of like a Monero, like a quantum-resistant Monero. So there are teams who are working on this. I think Ethereum is just such a big beast that nobody's really been able to replicate Ethereum to be quantum-resistant. And so I think that's probably one of the largest kind of, or most interesting problems, because we've already developed all of the kind of, Ethereum has the network effects and it has the economy to reflect that. And so transitioning, our current industry to, you can kind of imagine like our current framework to be quantum resistant in Ethereum is probably the most interesting and challenging task. But yeah, I think there are ways to do it. And it seems like Vitalik is also thinking critically about this. So.
All right, thank you. Good presentation, by the way.
Thank you very much.
Any more questions for Christopher? Okay, thank you, Christopher.
Thank you.
And now we are going to take a break for 30 minutes.